Autopilot. This is video number 3. We've been talking about the general knowledge in video number 1. Video number 2 was about the lateral navigation. Today we are talking about the vertical navigation. If you're interested in this topic, follow me into the Pilot Lounge. Today we are talking about autopilot vertical modes. First of all, before starting, I shall remind you that there is a video disclaimer. I shall ask you to be familiar with this video disclaimer, which is linked in the description. And then I shall remind you the importance of like and subscribe. Thanks to your likes and subscribe, I can keep this channel free, and especially sharing this video with your friends will help me to keep this channel free of paying content. So the target at the moment is to try to keep this channel free of paying contents. So thank you very much for doing so. And now let's move to the vertical navigation of the autopilot. Talking about vertical navigation of the autopilot, we have to add one thing. And this thing to add is the control of thrust. But why? Well, because when we talk about vertical, unlike the lateral, the vertical is always connected with the speed of the aircraft. Even if the aircraft does not have an automatic control of thrust, there still is an effect of the vertical mode on the speed of the aircraft. And this is because the potential energy is connected to the kinetic energy. Let's take this roller coaster scheme that I will use to clarify what I'm meaning talking about kinetic and potential energy. So this is the roller coaster with a cart, and we presume that you are sitting inside this cart. Okay, so this is you sitting inside the cart, and the cart of course is moving upward. The reason why it's moving upward is because there is a motor, let's pretend an electric motor, that is pulling up the cart. There we go. I also draw a cable. The cable is the reason why the cart is moving up. Now the cart reached the top of the roller coaster, but for some reason we pretend the cart at this moment is not moving, so it's in a perfect equilibrium, standing still there, and you enjoy the view because here is very high. We pretended the height, just to make it simple, we call it 100 meters. Okay, so you are enjoying the view from 100 meters. This 100 meters is actually what we call potential energy, and that's why I will write down EP, potential energy. Okay, at this point I arrive, and with my finger I just push a little bit, tick, and push a little bit your cart, and now your cart starts moving, and of course it starts accelerating. As we are halfway through the descent, your cart will be obviously half of the altitude, so we can call it 50 meters, but at the same time it will have a speed, and just to make it simple we'll call the speed 50 kilometers per hour. Now, once the cart reaches the bottom of the roller coaster, the height will be 0 meters, and the speed will still be increased. For simplicity, I'll call it 100 kilometers per hour. Now you see that if I come and say, you see how powerful is my finger? With just one finger I caused your cart to go 100 kilometers per hour. You know very well that the energy was not coming from my finger. The energy that caused the car to go at 100 km per hour was the potential energy. So I just transformed potential energy into kinetic energy. And that's why this 100 km per hour, I will call it EK, energy kinetic. Okay, so all we did on the roller coaster, all we do is transforming potential energy into kinetic energy, and then back on the next climb we will transform again kinetic energy into potential energy. Now it wasn't my finger, as we said, that caused the roller coaster to go so fast. It was the potential energy, but where this energy came from? Well, it came from the electric motor. At the beginning of all this process, if you remember, there was an electric motor that pulled up your cart.
There normally is a very powerful motor, but it still takes time because engines, same of the engine of the aircraft, cannot deliver an infinity amount of energy. So the energy that the engines can deliver is limited, and because the vehicle, in this case the cart, or in our case the aircraft, is much heavier, or anyway is very heavy compared to what the engine can deliver in terms of power, then the result is that we need to use time. We need to keep the engine running for a given amount of time in order for the engine to slowly deliver the amount of energy that we want to collect into the potential energy. So basically, while it's easy to transform potential energy into kinetic and kinetic into potential, when it comes to engines take time to deliver the energy. So the sum of potential energy and kinetic energy might increase, but this will take time.
So from the roller coaster scheme, being a pilot, you should know that control of the speed is an extremely important thing. Unless your aircraft has an angle of attack indicator, in which case I will tell you controlling the angle of attack is one of the most important items on your aircraft. At this point, if I want to make an automatic control of the aircraft, obviously I have to think about a system that controls the speed. So in the autopilot system, when I have an automatic control of thrust, the basic rule is that there must always be one of the two channels. Would it be the pitch? Would it be the automatic control of thrust? But there must be always one of the two channels which is controlling the speed. And that is the basic rule. This means that every time I change my vertical mode, if my vertical mode is maintaining the speed, then the auto thrust will have to maintain something else. If my vertical mode is maintaining a different parameter, like for example level flight, then if it's level flight, the thrust control must absolutely be the speed, cannot be anything else than maintaining the speed. For this reason, when we're going to discuss the slaving logic and the slaving loops of the autopilot, you will see that we will add an additional box. And this additional box is what is the autopilot output to the auto throttle. And that's important. The auto throttle is, or the auto thrust, is an output to the autopilot. Meaning that when something is an output, the computer itself does not know how the output is performing. Yes, there are some control loops, so there is a feedback from the thrust to the autopilot, but as a matter of fact, generally speaking, we should consider the fact that the autopilot, or the vertical control of the flight, does not take account of what is the performance of the thrust control. So when I insert a vertical mode, there is just an output going to the auto throttle. Is then the auto throttle working properly or not is not a problem of the autopilot. For what concerns the vertical navigation of the autopilot, we basically have again few modes, but those few modes are basically three. The first is the spare autopilot, constant pitch of the aircraft. Once again, this is the autopilot disconnected for the Airbus, and this is control with steering for the 737, although the Airbus has actually not a real pitch hold, is more a G acceleration hold. But anyway, what happens is that in the practical point of view, it will look like the Sperry autopilot, so pitch hold, okay? For what concerns the 737, once again, it has to be stated that there is the possibility to use as a control with steering. So when you use constant pitch and constant bank, or it might be just the reversion mode or the deselection mode. So when you deselect a mode, the autopilot will revert into control with steering pitch if it was a deselection of a vertical mode, control with steering roll if it was a deselection of lateral mode.
So here I have engaged on the 737 the control with steering. Control with steering is a function of the autopilot. Although when control with steering is engaged, the aircraft will behave as if I am in manual flight, which means I can use the flight director, or I might decide not to use the flight director. In this case, the flight director is off, of course, and with the control steering, I basically have a spare autopilot, so the autopilot is maintaining the pitch, maintaining the bank angle. The only difference is that I can change the selected pitch or the selected bank angle by applying a force on the primary flight control, so on the yoke. At the moment I'm maintaining more or less 3 degrees and a half, which is level flight. Actually maybe it's a bit too much. I will decrease slightly to around 2 degrees and a half, 3 degrees. And the test that I will do is that I will increase thrust. Okay, one of the effects of increasing thrust is that the aircraft has a tendency to go pitch up. Let's see what happens, because the pitch hold, as we said up to now, pitch hold should make the aircraft maintaining the pitch. So let's start this experiment. We have currently 2 degrees and a half, and I'm increasing thrust. There we go, thrust has been increased, and you see that the pitch is actually rising. This flight simulator is a bit exaggerating. Normally control with steering is much more precise, should be maintaining 2 degrees and a half more precisely, but you see that as a matter of fact the autopilot is bringing back the pitch to 2 degrees and a half, so we had 2.5 and still we have 2.5 now. Now obviously with 2 degrees and a half at this increased speed the aircraft would be climbing. Before we were in level flight, but as you very well know, if you increase the speed you require less pitch, and so maintaining 2 degrees and a half the aircraft is climbing. But as a matter of fact we maintained the pitch constant despite the variation of speed, so the autopilot is not tracking a path, it's not tracking an altitude, not tracking a vertical speed or climb or something like that. The only thing we're tracking is 2 degrees and a half, the pitch that I have set in the beginning. Now I'll do the same experiment by closing the thrust and see what happens. Again, when I close the thrust the aircraft should have the tendency to go nose down, so I expect again the simulator to go a little bit nose down. You see I've closed the thrust. It's not that significant as it was when I applied thrust, but you see the pitch went a little bit down. We were 1 degree and a half, 2 degrees, and now the autopilot again, control with steering, is maintaining 2 degrees and a half. So basically the autopilot attempt to maintain constant pitch. As I decelerate, of course, with that constant pitch I won't be able to climb as I was doing before, and eventually if I go below 220 knots I'll probably end up descending. There we go, we're passing 220 knots. I keep the thrust idle so the aircraft keep decelerating, and you see that the autopilot is maintaining more or less 2 degrees and a half, a bit less. I tell you, in reality the control with steering is even more precise than this. We are losing the pitch by more or less 1 degree. Normally the autopilot, or anyway the control with steering function, is much more precise than this. There we go. So the scope of this exercise was just to demonstrate that the control with steering is maintaining the pitch constant. I am trying to replicate this exercise on the Airbus 320. You see, I close the thrust, we have little tendency to go nose down. That's the pitch down effect of the thrust. And then as I add thrust, now there's gonna be a little tendency to go nose up, but very small, because the aircraft has been set at 5 degrees and a half, and we are maintaining 5 degrees and a half. So it's constant pitch attitude maintaining. Okay. Now this demonstrates one of the limits of the home video games and flight simulator, because this behavior is a perfect demonstration of the correct 737 behavior. So if this would be a 737, this would be absolutely correct. A little tendency which is immediately compensated by the autopilot. Now as you see here, keep accelerating, the aircraft keeps 5 degrees, so we find ourselves exactly in the same position where we were with the 737. The autopilot is maintaining constant pitch. But what is the problem there? Well, the problem is that the Airbus does not behave like this in reality. So we have to go into the real aircraft or in a certified simulator to give a look to the correct behavior of the Airbus in monoflight. Here we are on a real Airbus. Actually this is a certified flight simulator, so don't worry, there is no pilot sitting at the controls, so nobody is touching the flight controls, and you can see from the flight mode annunciator that autopilot is disconnected. Okay, I also disconnected now the auto thrust. What I'm gonna do is that I'm gonna bring the throttle to idle. There we go, monoflight. You see that we are in 5 degrees, which goes to 220 knots, same in the flight simulator I have at home, was the straight level flight. The speed is decreasing, Look at what happened actually. The pitch is slightly increasing. You see, we're nearly reaching 6 degrees in pitch with thrust idle. Now I'm gonna add the thrust. As we say, the aircraft has little tendency to go nose up, but this increased nose up is actually the result of the deceleration I had. The aircraft is actually compensating with the automatic trimming. Let's see what happened as the speed increased. In the home simulator it was maintaining 5 degrees. Look at the pitch, is now decreasing. We are 4 degrees, we're nearly 2 degrees now. You see the pitch is going down quite fast, I would say. With the speed increase, the pitch is going down. Still the altitude is climbing, so what is the aircraft tracking at this point? Is it tracking the altitude? It's not tracking the pitch. Well, the fact is that the Airbus logic is not really a spare autopilot. As we say, the flight guidance computer is much more complex. It does not take just one item, like the vertical gyroscope, as a reference. What we're tracking here, yes, is the attitude, it's constant attitude, but it's also compensated for constant G. Now here I'm just showing that with the thrust idle, the trim is moving nose up, so it's automatically trimming. We are keeping constant G acceleration on the aircraft. To keep a constant G acceleration, as the speed increase, obviously we have to reduce the pitch attitude. So you see now we're nearly 2 degrees and a half at 280 knots. Now thrust is idle, so we're reducing thrust, and again, to compensate the G, the aircraft is going again nose up.
Concerning the pitch hold of the Airbus, it's worth saying that there are flight envelope protection applicable to the pitch as well, but again, in that case, we are talking about flight envelope protection, not really flight guidance functions.
Paolo's Pilot Lounge. Like and subscribe now.
For what concerns the other methods, the methods are very simple. It's either a speed descent, constant speed descent, or either a geometric descent, so a geometric control of the descent. So the speed descent is quite easy. Imagine that I have control of power on your aircraft, and at some point I tell you, maintain 80 knots, okay? And at this point I put full power in, full throttle in. Well, what you have to do to maintain 80 knots? Obviously you have to go with the nose up. And if I take all the engine cut off, is what your extractor does, for example, when he simulates an engine failure. Well, what it does, it puts the engine nearly idle power, and now you have to maintain a constant speed, and the only way to maintain a constant speed is descending, okay? And that is a constant speed descent. You don't know what's going to be the vertical speed. All you do is keeping the speed, okay? The other method is a vertical speed, or not a vertical speed, could be an angle descent, could be an FMC generated path, but in all cases we are talking of a geometric descent.
In this graphic we see an aircraft descending on a 3 degrees descent. Now we can only control the vertical speed, so basically every time we are in vertical speed we actually are controlling an angle of descent. Now if the speed of the aircraft changes, obviously the vertical speed will correspond to a different angle of descent. The only way to have a constant angle of descent is to adapt the vertical speed to the speed of the aircraft. So advanced computing might calculate what is the adapted vertical speed at the changing of the aircraft speed. Of course an FMC can do that, an FMC can control the aircraft on an angle of descent, but it remains the fact that controlling the angle of descent, so being on the VNAV vertical profile, or controlling the vertical speed, doesn't change anything. And at the end of the day, maintaining the altitude is nothing else than a vertical speed of 0, so maintaining all the altitude remains a geometric vertical guidance of the aircraft. Let's therefore give a look to which would be the slaving parameter for a vertical control, vertical speed control, and what will be the logic for the flight control computers. The outer loop would be, of course, maintaining the selected vertical speed. The inner loop would just limit the rate of change in pitch in order to avoid excessive changes in G load. On first engagement of the vertical speed mode, the initial part is just determine the direction in which the body angle has to change, whether it's nose up or nose down, in order to achieve the positive or negative vertical speed that has been selected. The capture phase is to reduce the change in body angle in order to maintain constant pitch, and in the tracking, of course, the pitch remains basically constant and a small adjustments made in order to maintain the selected vertical speed. What is the output that the flight control computer will send to the auto throttle or to the auto thrust? The output will be speed, so the speed will be controlled by the automatic control of thrust. Good, let's give a look to the vertical speed. The vertical speed selected is displayed on the MCP. The function of the vertical speed, you see you have a magenta dent that show you what is the selected vertical speed. I was saying the function of the vertical speed is to have the aircraft climbing at a selected vertical speed. So I would say there is quite obvious. You see we selected 500 feet per minute. The aircraft is climbing at 500 feet per minute. Now the vertical speed is normally used, we say VS for finesse. Why this? Is because the vertical speed leave as an output the speed in control to the automatic control of thrust, so to the auto throttle. This means that the autopilot use the auto throttle as an output, meaning that it will not take into consideration the fact that the auto throttle can or cannot maintain the speed. So for example, if I go and increase the speed at this stage, of course the auto throttle will give me the maximum thrust available, but will not be able to fly this as high speed with 500 feet per minute. Now the speed is increasing because the rate is small, but I select a higher altitude. And now I select a higher vertical speed. Let's look what happens. You see, with 6,000 feet per minute selected, now the thrust is already at the climb thrust, so there's no much I can do. And with this very high rate selected, well, it's going to take a while for the aircraft to reach the rate. Normally in the real aircraft the vertical speed is a bit more aggressive, a bit more responsive, I would say. But you see that what happens, as the rate increases, the climb thrust is not even enough to maintain the speed, and now what happens is that the speed, instead of increasing towards 330 knots, is decreasing. It will start decreasing. You see it's going down. So making use of vertical speed for high rate of climb or descent is quite dangerous, because you see in this situation I'm bringing the aircraft towards the stall, and the stall, or anyway the loss of speed, will occur quite fast. Now there are reversion modes that will cause the aircraft to go in level change at the minimum speed, but it's a reversion mode that does not give you any real guarantee that the system will actually work. So obviously using VS here in the simulator, it's much easier than what is in the real aircraft. In the real aircraft, of course, the loss of speed is going to be quite significant and quite faster. So remember, VS for finesse, you will use VS only when you have to make smooth corrections and not such a large correction. Okay, so what I can do now is click Alt hold, and it's gonna maintain the altitude at which I was. You see the aircraft is rapidly now decreasing the pitch, because otherwise I was about to stall. Now with Alt hold, of course, the speed is going to increase rapidly, because also in Alt hold the speed remains managed by the auto throttle, so the auto throttle remained in MCP speed. Okay, now lower altitude, for the descent I would say that's no much to say. For the descent is exactly the same condition we saw before. So I click vertical speed, select the rate of descent I want. We say it again, make it a finesse, so no more than 1000 feet per minute, and this will allow you to have controlled the speed. Of course, now with this rate I have controlled the speed. If I want to accelerate, I will get a bit more thrust and the aircraft accelerate to 260 knots, so it's not a problem. Okay. Alright, so you see 500 feet per minute works very well. The auto throttle is controlling the speed, and it managed to accelerate to 260 without any difficulty, and now the thrust is coming back again because it reached the speed. If I go with an increased rate of descent, already with 1000 feet for example, if I attempt to reduce the speed to 220 knots for example, you're gonna see that it's nearly impossible. The aircraft cannot descend at 1000 feet per minute and lose the speed and bring it to 220 knots. You see the green arrow is very small, and basically the speed is gonna go steady. It's not really gonna stabilize. Okay, so you see 260, 250, and in real life is gonna stay around 250, 240 knots, and even in the sim you see speed is coming back but extremely slowly. So you see we're nearly 1 minute gone and still descending 1000 feet per minute, and after 1 minute we didn't really manage to lose any significant amount of speed. We still 240, 243, and the speed is very slow in decreasing. So what I want to say is that even with a finesse, even with 1000 feet per minute, does not say that you're gonna have a proper control of the speed. If the air traffic control assigns to you 220 knots vertical, 220 knot speeds, you should reduce significantly the vertical speed, like 500 feet per minute, in order to be able to have a reasonable deceleration and reach the desired speed quite fast. So don't assume that 1000 is a good vertical speed in all circumstances, because unfortunately it is not. If I select a very high vertical speed, then the autopilot will lose control of the speed. So now I'm selecting something like 6000 feet per minute. Okay, and with 6000 feet per minute, again the aircraft is quite slow in losing the pitch. The real aircraft is a bit more aggressive with the pitch there, but what happens is that I'm going to lose control of the speed is going to increase. Again, there are reversion modes, but you can't really rely on the reversion mode. The reversion mode itself is a protection to avoid the aircraft keep increasing towards the overspeed, but is not giving you any guarantee against the overspeed itself. You see that now we lost control of the speed is increasing, and eventually will reach the overspeed. In this case, for just 1000 feet change, I'm gonna select another, once again, 1000 feet change. In this case, what I could do is rather selecting a vertical speed, so maybe 1000 feet per minute. So 1000 feet per minute, this time the sorry, if I don't pull, there we go. You see I've pulled, meaning that I've selected VS 1000 as shown on the FMA. The aircraft is climbing 1000 feet, alt is blue, and the speed mode, the thrust mode, remains in speed, meaning that the thrust are managing the speed. So this is going to be a fairly smoother way of climbing. If I want to be even smoother with passenger, I could select a lower rate. It's not recommended. Most of the busy airports require at least 1000 feet per minute rate of climb and descent in terminal area, so probably 1000 feet will be the correct number. Let's see now if I select a much higher level. Well, maybe I selected too much, but level 230 for example, and for some reason I decide to climb at a very high rate. So once again I select 6000 feet per minute. Same as we said, same as any other aircraft, what happens is that the autopilot attempts to maintain the selected vertical speed, because as a matter of fact the speed is an output, the automatic control of speed is an output. So you see that the of course the auto thrust goes and gives us the climb thrust, which now is 84.7, but despite we having the climb thrust set, there's not much the auto thrust can do. We start losing the speed in the attempt of maintaining the vertical speed. Now of course there will be reversion mode, the Airbus as well will have protection for the stall, but still the reversion mode are not there or not designed with the intention on having pilot using it. So selection of a high rate of climb or high rate of descent is not a good idea, and should be avoided no matter the aircraft you're flying. So for this reason I will now reduce the rate, because there's no No intention now in looking at the reversal modes. We're not discussing this in this video.
Paolo's Pilot Lounge. Like and subscribe now.
Flight level change, climb and descent, open climb and open descent modes. Well, we have seen the vertical speed, the flight path angle, which are modes that use constant angle. Well, now the angle only depends on the thrust setting. Let's therefore give a look to what is this leveling parameter on the open climb, open descent. Of course, the open loop would be maintaining the airspeed, which already means that this cannot be maintained by the thrust. You can't have two systems trying to stabilize the same parameter. It simply wouldn't work. It's like if you try to draw a line on a piece of paper moving a pen, and at the same time I'm moving the piece of paper underneath, trying to draw a circle, for example. But none of us would succeed in its function. So only one system can control a parameter. The loop can be controlled only by one element, and this element is the pitch. Obviously, the inner loop will be maintaining the stability of the aircraft, limiting the G-loads and limiting the change in body angle of the aircraft. Now, the initial action when you engage an open climb or an open descent is to determine exactly if this is an open climb or if this is an open descent. So what should I do to do this? Well, simply to determine if the selected altitude is higher or lower. So all we do, we determine if selected altitude is higher or lower, and then actually for the pitch itself, it doesn't really mind. The aircraft doesn't care whether it's a climb or descent, because all we have to do is to maintain the speed. So if it turns out that the thrust is going idle or is being reduced, to maintain the speed you have to descend. And if it turns out that the speed is increasing, well, because the thrust is being increased, to maintain the speed you have to climb. But what is important in this case is the output to the thrust mode. The thrust mode must be in constant thrust, and this must be a retard and therefore idle thrust if the selected altitude is lower, so as to produce a descent, and it must be the full climb or the N1 full climb thrust for the climb, so that with the engine producing the maximum thrust, I will need to pitch up in order to have the aircraft climbing. The strong relation of the level change mode with the speed is shown by the fact that level change, same as VNav, they are located in the speed area. So this enhances the fact that this is a speed control. While altitude hold and vertical speed, they are located in the altitude area of the mode control panel. This further enhances the concept that if the autopilot takes care of the vertical profile, you have to think about the speed, or the auto throttle has to think about the speed. If you have the autopilot taking care of the speed, then it's you or any other system that has to take care of the vertical profile. The level change mode is a mode that we said will compare the selected altitude with the current altitudes and will climb a constant speed commanding to the auto throttle either the maximum, either the minimum thrust. Now in this case I have selected level 140, which is higher than level 70. So what I do, I click level change, the system compares current altitude 70 to the selected altitude 140. It is higher, so let's go at maximum thrust. You see that I get the N1 on the annunciator panel, on the fly mode annunciator, and I get MCP speed. So the aircraft is now climbing 220 knots with N1 with the maximum thrust for the climb. Now, if I select a faster speed, obviously the aircraft is going to reduce the pitch, because the only way to maintain 260 knots is reducing the pitch and using some of the energy of the engine to increase the speed rather than increasing the altitude. So by doing this, basically I manage to climb. Now what happens is that sometimes you are in manual flight with flight director, and what happens is that the instructor asks you to make a climb. So you will ask to the other pilot which vertical mode you want. For example, you will ask for level change. Now if you ask for level change and you are in manual control of the thrust, as I did now where I disconnected thrust, if I close the thrust lever or if I don't give enough thrust, what happens is that the speed, as you can see, is decreasing, and the aircraft now has to descend in order to recover the speed. So it could be that in level change the aircraft started descending, as it's doing now. You see the aircraft started descending, because in order to recover the speed we have to descend. So that's a correct functioning of the level change. As a matter of fact, you see the aircraft is trying to reduce as much as it can the rate of descent, but it's losing the speed, and the only way to avoid losing speed is to keep descending. So it will eventually even increase the rate of descent and will continue descending. So the level change itself does not guarantee to you that the aircraft is climbing or descending towards the selected altitude, because the fact that the aircraft climbs or descends is exclusively connected to the selected thrust, and in this case I selected a descent thrust and the aircraft is factually descending. If I set, for example, a thrust which is more or less the cruise thrust, something around 60% for the 737, well, what will happen is that the aircraft is gonna basically level off. Now we're gonna end up in a level flight. Probably we have to recover the speed, so I give a bit more thrust. There we are. So I keep the level flight, and basically you see what happens is that if I don't give thrust, so if I keep the thrust for the level flight, what the autopilot does is just flying level, so we're not climbing. So sometimes it happens that in level flight, manual flight with flight director, I ask the pilot to make a climb and the pilot forgive to give thrust, so just give it just a little bit of thrust, as I'm doing now, around 72%, which is a bit more than what you need for level flight, which is in the range of 55-60%. And you see what happened, we got a very small climb and the pilot wonder why we're not climbing, and eventually I ask you why we're not climbing and the pilot can't find an answer. Well, the answer is very simple: you didn't select thrust. If you select the thrust, of course the aircraft will have tendency to increase the speed. As you see, we're increasing the speed now, but the response of the flight director is to command an increase in pitch, and the increase in pitch will produce the climb. Okay, the very same way, if I am in level change and I reduce the selected speed, with the reduction of the selected speed, now in order to make 220 knots I even have to climb faster. So reducing vertical speed, reducing select the speed and keeping the climb thrust on the engine will have the effect of having very high rate of climb. But as a matter of fact, this is a fairly reasonable or fairly safe way of climbing, because once I reach the selected speed, the aircraft is going to maintain the speed with the pitch. So even if the thrust is not enough for what I want to do, well, we're gonna maintain the selected speed. Okay, good. Let's do the same example in the descent. Not a big deal. I'm still in manual thrust at the moment. I select a lower altitude and I go level change. Once again, the aircraft will use the pitch to make the speed. At the moment, the thrust is idle, but the speed is higher. So you see, the aircraft is not descending and is eventually even climbing a little bit, because for as long as I don't make 220 knots, the aircraft will not descend. The pitch is chasing the speed, and it takes time actually on this aircraft to lose the speed. So for as long as I don't have 220 knots, the aircraft is not going to descend. Now you will see that we reached 220 knots and we're going to start descending, because of course with 37% we either lose the speed, either lose the altitude. And as a matter of fact, flight level change is a safe mode, will maintain the speed. So you're not going to bring the aircraft to a stall in this case, but we're going to start the descent. You see, we reach the speed and the vertical speed now increase, we start pitching down, we start doing the descent. Yeah, the very same way, if I increase the selected speed, for example 280 knots, in order to have an increased speed, well, the aircraft has to go further pitch down, and therefore further increasing the vertical speed in order to lose more altitude, have an increased airspeed and reach 220 knots. So we're trading altitude for speed at the end. That's the conservation of the energy between altitude and speed. Now you see that we have 3000 feet per minute. The speed is increasing, but as I reach the selected speed, of course, I don't need to trade altitude anymore for speed, so I just need to lose the energy or the altitude which is needed to maintain the speed. So the rate will slightly reduce now. You see, we're reaching 280 knots, we got 2000 feet, it's gonna stabilize around 2200, something like 2200 feet per minute. And that's a stable rate of descent. Same thing, if now I selected a lower speed, same as it was at the beginning of the descent, by selecting a lower speed, the aircraft has to go nose up, and eventually it will even stop the descent in order to reduce the speed. So now I'm trading speed for altitude. So I'm even climbing now in order to maintain the speed. Well, I select an higher speed in order to descend a bit faster to the selected altitude. I can select, for example, level 90, so we reach the level earlier. And now, you see, I am in auto acquire. As soon as I go in auto acquire, now the thrust became responsibility of the auto throttle. But because the auto throttle is disengaged, well, now the thrust is my responsibility. I have to personally think about adding thrust. If I don't do that, that's the auto throttle channel that tell me that there is nothing on the auto throttle. So if I don't add thrust, what happens is that obviously we'll end up into a stall. Alright, let's see, for example, if I make an improper use of level change. So something that normally would be done with vertical speed, because I said vertical speed is for the finesse, is for the small change of altitude. Let's say I want to climb level 100. Now what happens is that as I press level change we understand that level 100 is above our selected level and will go full thrust. This will be quite uncomfortable for the passengers, because now we're going full thrust, so they feel accelerated. The aircraft will start climbing in a quite sharp manner with a high rate of climb. You see, we got now 3000 feet per minute, and as soon as we started climbing, now we have to go again with the nose down. So there is a reduction in the G load, there is a reduction in thrust. So this maneuver was quite abrupt. We reached, in the time frame of few seconds, 3000 feet per minute. Basically in the time frame of 20 seconds we went from 0 to 3500 back to 0 feet per minute, which might be quite uncomfortable for the passengers. And this logic will apply to any altitude change. So even 1,100 feet, if I go level change, the system is gonna go full thrust. There you go. You see, I got, well, it didn't even go N1, but I should be going N1. Let's try it again. This is a simulator problem, sorry. Let's try with 400 feet. If I go level change, there we go. We are in LNAV, in N1, MCP speed. We're climbing full thrust, and we're reaching 2,000 feet. You see, 2,200 feet, and now back to zero. That's fairly uncomfortable for passengers. So, if you have to make such a smooth climb descent, obviously the correct method would be like just 400 feet per minute climb. The correct method would be using VS, indeed. So, you see, with 200 feet per minute, now it's gonna take to gain this 400 feet at 200 feet per minute is gonna take 2 minutes. It's gonna be extremely long. Basically, no passenger on board is gonna realize that we are climbing or descending. Okay. I select higher altitude, flight level 100, and I go in the open climb, which corresponds to the level change. Now, the open climb, open descent has exactly the same logic. The system detects if the altitude selector is higher or lower than what I have at the moment, and will determine if we have to go full thrust or idle thrust to produce a climb or a descent. So, in this case, the altitude is higher, so the system is going thrust climb, as you can see on the fly mode initiator. I see open climb, and on the Airbus I see that altitude is blue, altitude is arm. On the 737, of course, this altitude blue is not shown because the altitude is always arm, but is not shown. Alt star is the acquisition phase of the altitude, where we smoothly start reducing the rate, and as soon as I get alt star, I also get the thrust mode going back into the speed mode. Again, this usage of an open climb for such short climb might be not the best method, because still it gives quite a strong acceleration. It is true that the Airbus has a number of logic that makes the flight smoother, more comfortable for passengers, resulting in a smoother change in altitude, but still, open climb probably wasn't the best solution. If I pull back toward me again, I activate the open descent, so the system detects that the selected altitude is lower than our current altitude, and what happens is that we start descending. We see the engine going to the idle. You see we got thrust idle shown on the fly mode annunciator for the thrust mode. We got open descent, altitude arm, and of course heading. So we are now descending. Of course, same as we did the trial on the 737. If I increase the speed, what happens? Obviously, because the thrust remains idle, the only way to have a higher speed is to pitch down farther and convert more altitude into speed, and that's what we're gonna do now. You see the rate of descent is increasing, the speed is increasing, so we have an increased rate of descent in order to increase the speed. There we go, we got more or less 3,700 feet per minute. The speed is increasing quite fast. You see we're gaining easily 5 knots every 3 seconds, something like that. And without the speed, as we reach the selected speed, what will happen, of course, is that we reduce the rate of descent, because we just want to maintain the speed, we don't want to accelerate anymore. Of course, if the very same way I elect to fly a lower speed, what will happen is that the aircraft will start pitching up in order to reduce the speed, and therefore we lose less altitude, we lose less potential energy in order to waste the kinetic energy and have the speed reducing. You see the rate is descending, we got 900 feet per minute, and if this is not going to be enough, the aircraft is going to reduce even further the rate to 500 feet per minute. At the moment looks like it's going well, so the aircraft operates smooth change. If you see, this is actually the Airbus, as a matter of fact, thanks to the flight augmentation computer, which is capable of more complex calculation, is making actually smoother corrections. So you see that at the moment 900 feet per minute is a reasonable compromise among loss of speed and loss of altitude, and that's what we're maintaining. Other autopilots will eventually even climb in the attempt of reaching 210 knots faster. So you see that in order to have a continuous deceleration, the aircraft needed to reduce the vertical speed. Now we are 700 feet per minute. The speed is approaching the selected speed of 210 knots. So as we reach 210 knots, same thing, we're going to have a small increase in the rate, because this time we're going to use again the potential energy, so the altitude, in order to keep constant speed. At the moment we are trading off speed in order to match 210 knots, so we're losing some kinetic energy, and in order to lose this kinetic energy we have to reduce the loss of potential energy. There we go, we arrived at the selected speed, and you see the rate is increasing again, 900 feet per minute, 1000. That's more or less the rate we're going to keep, around 1100 feet per minute. That's at this speed, 210 knots. Clean configuration is more or less the rate that the aircraft maintain, 1000, 1200 feet per minute. Altitude hold mode, it's obviously a function of the autopilot, which is preceded by the altitude acquisition mode. So normally we are able to maintain the altitude using the autopilot, but this function is automatically engaged, so the altitude hold is automatically engaged as a result of acquiring the selected altitude. For what is the logic of functioning of the altitude hold function, we can see that obviously the outer loop is maintaining the altitude at which the mode was engaged, and the inlet loop once again as a function of stability, so to limit the pitch change angle. Now the flight control computer logic will be very simple. On the initial point we will memorize the altitude at which the mode was engaged. For the capture phase, of course, we start doing a smooth change in pitch in order to go back to the altitude that was memorized, and in the tracking phase again is minimum pitch adjustments in order to maintain the memorized altitudes. Now we already said that what happens is that the level flight at the end of the day is a geometric mode of flight, is a angle of flight 0, and therefore whenever we have a geometric way of flight, of course the thrust mode will be speed, so will be the auto throttle or the auto thrust maintaining the speed. Now it is worth saying that the altitude hold function will go together with the function altitude start or altitude acquire. Here there are some technical differences between Boeing and Airbus, as altitude acquire is a specific function for Boeing, altitude start still is part of the altitude basically. So yes, there will be especially a difference in the area which stand here in the initial and then capture phase on the Airbus, because these basically the fact is that on the Airbus you can't really directly engage altitude green without going from a capture phase or a eventually extremely small, but still you can't go directly in altitude hold, you must have a capture phase, while on the Boeing the two phases are separated, are two different vertical modes. But for as far as is concerned on the subject instrumentation, we can consider that there is no difference among the two aircrafts. First of all, altitude hold as the function of maintaining the altitude. That's what we're doing now, we're maintaining the altitude. If I select a new altitude, the altitude hold, if you remember the rule, is that it takes a picture of the altitude we have in the MCP, or actually we have on the aircraft as we reach that altitude as we push the button. So once the button is pushed, it takes a picture of the altitude and maintains the altitude. So you see that what happens is that here I have selected a new altitude and I'm still in altitude hold, I'm still maintaining 5,000 feet, absolutely nothing happens. Well, I can see on the flight mode consider that automatically the system armed for me a vertical speed mode, meaning that if I go and turn the vertical speed knob, I can start climbing and descending directly in vertical speed. But if I am in altitude hold, and I'm gonna go back to altitude hold, what happens is that the aircraft is maintaining the altitude. So altitude hold is a function that indeed maintains the altitude. Now, I select vertical speed. And we start climbing. That's at a fairly high rate, okay? And what happens if I command altitude hold? As I said, we take a picture. So at 5.5, now I selected altitude hold. So the system took a picture of 5,500 feet. And now the function of altitude hold is to maintain 5,500 feet. So you see that we are descending back to 5,500 feet. And that's what we're doing. We're approaching 5,500. Now we are maintaining 5,500. So that's exactly what we say. Altitude hold, memorize the altitude at which the system has engaged. And there's nothing to do with the selected altitude, because once it's memorized, I can change the selected altitude as much as I want. Nothing happens. The altitude acquisition modes, which is Alt Star or Altitude Acquire for the Boeing, are modes that cannot be selected by the pilot. Is the automatic function that allow the aircraft to transit from the current rate of climb descent as a result of a selected mode, which could be vertical speed or level change, for example, into the altitude hold mode. So it's a progressive reduction of the vertical rate in order to reduce the rate of climb or descent and transition into the altitude green or altitude hold function. This altitude acquire function is nothing else than a vertical speed function. So during reselection of altitude, different behavior could occur depending on Airbus, depending on Boeing, if I change the selected altitude during the altitude star or the altitude acquire function. So we can say that the function of maintaining the altitude is the straight line of flight is this black line, which will be performed with the altitude hold function. Okay, this is the altitude hold. That's what altitude hold can do. But the question is, how, when I'm climbing from a climb, how do I bring the aircraft from this steady rate of climb onto this steady level flight? So this maneuver there has to be done by a different function, and that is the altitude star or the altitude acquire function. Okay, how does this function works? Well, it's very simple. It measures the rate of climb of the aircraft once we are approaching the altitude. So you see, I could have a very shallow rate of climb, or I could have a very steep rate of climb. And basically what we do is drawing a circle. So you can imagine that the system is drawing a circle that goes from current rate of climb to 0. And once this circle, there's an arc of a circle, okay? And once the circle connects the current rate of climb with the altitude, well, the altitude acquire function or the altitude star function engages. So you see that here in this case, the altitude acquire will engage at this altitude, which could be, I don't know, 400 feet before, okay? In this case there, because I'm coming in with a very shallow rate, it could be that the altitude acquire function will engage, I'll change color, will engage in this red case at a later stage. So probably it will just engage 200 feet before, because the arc of a circle is just a small portion, okay? Well, in this case where I'm coming in with very high rate, and I'll change color again, I'll take the blue case here, where I come in a very high rate, I have to do a very long portion of the circle, okay? And actually this circle is even a smaller range, but anyway, that's the idea. So basically the altitude acquire will engage very early, like 1000 feet before. So if I ask you, when does altitude acquire engages? Well, it could be here 200, it could be 400, it could be 1000. Well, this depends by the rate of climb or descent of the aircraft. So with very high rate, altitude acquire or alt star will engage at very early stage. With a small rate, the alt acquire or alt star will engage at a very later stage. It could be that because the climb is very shallow, then the aircraft will transition directly into the alt green or the altitude hold function. One thing that has to be said is that the alt acquisition is a function that brings the aircraft, as we just said, from the current rate, from the rate that we have at the moment, so this rate here, we bring it from there, from this, 800 feet per minute to 0 feet per minute. So what happens if I change the selected altitude during the altitude acquisition? Well, if I move this selected altitude to a new line, so I put the altitude there. Now what happens is that this circle that I started drawing, this circle here, is not applicable anymore, because this circle would not bring to any selected altitude, given the fact that this white line here is not existing anymore. So I should cancel this black line here, sorry. This black line here is not existing anymore. So now the circle for which the altitude acquisition has engaged, so this circle there, I'll make it a bit sharper, maybe that's one is too much, there we go. So this circle there is not applicable anymore, because it's not bringing to the newly selected altitude. Okay, there is a difference there. So how do I sort out this problem? Well, there is no real solution, because it's two geometrical pictures, two geometrical figures that doesn't match together, don't cross each other. Okay, so there's no real solution to the problem, and the solution is reversion mode. So in the moment that the alt star, or in the moment that the altitude acquisition is engaged, what will happen is that the system is continuously reducing the vertical speed. As you can see, this is the vertical speed I have here, and this is the vertical speed I have here, this is the vertical speed I have here, and this is zero vertical speed. Okay, so what happens is that the system is progressively reducing the vertical speed. If I change, for example, this change of altitude acquisition occur at the moment I was with this vertical speed, what the system will do is to keep continuing climb with this vertical speed. So technically speaking, if I keep climbing with this vertical speed, I will reach the selected altitude at some point. So it is deemed to be like a safe decision to revert to the vertical speed during the altitude acquisition if the altitude is changed. Now the problem is, it could be that I was in this blue case where for some reason I say, well, I just have to climb by a few hundreds of feet, and so I was climbing very steep, okay, like 5,000 feet per minute, and then I decided for some reason to change the selected altitude again, and because the altitude was changed, now I was in this curve. And it could be that the system reverted in vertical speed when I had this vertical speed. Well, I should cancel a little bit of those drawing, because now it's getting a bit too much. So I was saying, it could be that at this moment there in time, I made this change in selected altitude. So I changed the altitude from there to there at this moment, and the circle was this circle. Okay, so this circle is not intercepting the newly selected altitude. And well, yeah, how do I sort out the problem? Well, we said I'm gonna keep constant vertical speed, but it's not said that keeping the constant vertical speed is a safe mode in this case, because it could be that here I was climbing 5,000 feet per minute, I went in reversion at 3,000 feet per minute, okay, but still 3,000 feet per minute is a very high rate, and it could be that during this segment I will lose control of the speed, because we said vertical speed does not guarantee to us the speed. Yes, it is a safe reversion to revert in vertical speed ideally, but it's not said that it's always a safe reversal. So use caution if you're climbing and selecting a new selected altitude. Give a look once again to the FMA, because the FMAs will tell you if the autopilot reverted in a mode which is inappropriate. Most likely what we should do in this case is just to go in the open climb or a level change and let the aircraft track the speed and maybe reduce a little bit the rate and then acquire the altitude at a different stage. So if we are to describe what are the logic of this mode, of course the outer loop will have a progressive reduction of the rate of climb or rate of descent, depending if we're coming from above or below, until bringing the vertical speed to 0. Then in a loop, we just limit the pitch rate change to avoid excess G-load during this maneuver. What is the flight control contributor logic? In phases initially is to monitor the vertical speed rate, actually to monitor the closure rate of the vertical speed, because we said that the engagement itself of the altitude star or altitude acquired depends from the rate, so it has to be monitoring the rate. If the rate is very high, then it will engage early. If the rate is low, then it will engage late. During the capture phase, it will perform this calculation and determine the leveling off time by progressively reduce the vertical speed towards 0. There is no tracking mode because altitude acquisition doesn't really have a tracking mode. The following tracking mode will be altitude green or altitude hold, obviously. This function, again, is a geometric function, so of course the thrust mode will be changing in speed, meaning that if we were climbing in level change, as soon as we transition to alt star, the automatic control thrust will move to speed, okay? If I change the selected altitude, you see that what happens changing the selected altitude during the altitude acquisition reverts in vertical speed. So now I've selected a lower altitude. At the moment that my selected altitude went through my current altitude, I actually caused a reversion into vertical speed. And 3000 feet per minute was the vertical speed that I had at that moment. This does not mean that the aircraft is capable of maintaining 3000 feet. It just means that in that specific moment, the aircraft had 3000 feet. So the system deemed as a safe outcome to switch me into vertical speed. The change into vertical speed occurred because I changed the selected altitude during the altitude star phase, during the altitude acquisition phase. Now, obviously, most likely what will happen is that the aircraft won't be able to maintain the speed and keep climbing 3000 feet per minute. So again, I could cause the stall of the aircraft. Now, if I realize something wrong and I want the aircraft to level off straight away, on the 737 you had the altitude hold function. Here the altitude hold cannot be selected, but you have a push to level off function which corresponds to the what is on the 737 the altitude hold. Actually, it's not exactly the same function, because if you remember what the altitude hold did on the 737, and it's what is doing the alt green on the Airbus, is to memorize the altitude at which the mode has engaged and to maintain that altitude. So the 737 would descend back to the altitude. What's happening on the Airbus is that you just select a vertical speed at 0, so we are maintaining the altitude via a vertical speed of 0 feet per minute. And of course, now that I realize what's the problem is that I changed the altitude and I need to descend. If I pull back toward me again, I activate the open descent, so the system detects that the selected altitude is lower than our current altitude, and what happens is that we start descending. In this different case, we see that the aircraft is descending in open descent. We're approaching the selected altitude of 7,000 feet. Of course, we see open descent, alt is blue, is armed, and as we reach the selected altitude, there we go now, we got altitude star, meaning that we are acquiring the altitude. Now we have the start of the phase where if I select a different altitude, I will revert into vertical speed. Finally, I get altitude green, so now the aircraft is maintaining the altitude, therefore I can change the selected altitude again. There will be no effect on the flight. I will remain on altitude green. Let's take another example of altitude change. You see that I'm selecting a different altitude from 7,000 feet. We are selecting 3,000 feet. In the very moment I select 3,000 feet, nothing happens. I have to pull toward me. Now I have open descent, and finally I see open descent. Altitude blue, so the altitude is armed. So changing the altitude would not cause the aircraft to descend. I have to take an action, either an open descent, either a vertical speed, either a managed descent through the FMS. but if I don't take an action, I just select the altitude, the aircraft would not actually climb or descend to the new altitude. The altitude hold has a transition function, which is the altitude star or the altitude acquire on the 737. The altitude acquire, or the altitude anyway, is always armed on the 737, so we should see continuously white altitude arm here. You should imagine an alt there, white, which is continuously displayed. Okay, you see that now we're approaching the altitude, we are in altitude acquire, and as we are in altitude acquire, we smoothly reduce the rate. So the function of altitude acquire is a smooth reduction of the rate. And you see, we're reducing the rate, reducing until reaching 7,000 feet. Altitude hold is engaged. The system took a picture of the altitude, and I can now change the selected altitude. Again, nothing will change. Nothing will happen if I change the altitude and select, for example, for level 80. Okay. In this specific example, we see the complexity of always reading the FMA. You see that we have the glide slope arm, we have 2,500 feet selected, so altitude is white, altitude is armed, and also vertical speed is armed. So we have three armed things in this moment, okay? Of course, we have to select one of those things, so now I start descending in vertical speed, so I just have glide slope and altitude remaining armed. The aircraft starts descending at the selected vertical speed because we are below the glide slope, so our intention is to intercept the glide slope. If the glide slope becomes captured, then the glide slope will become green, and we say it on the 737, the only function that does not have altitude arm is the glide slope. So if glide slope goes green, the altitude does not arm underneath. If otherwise we have a different vertical mode, the altitude always remained armed. You see that we are approaching 2,500 feet. What will happen obviously is the engagement of the transition phase, so altitude acquire is going to come in a moment. There we go. And after the altitude acquire, we will be in altitude hold 2,500 feet. If I select a different altitude at this stage, we will go in vertical speed. I have to wait until we have alt green, altitude hold. Now we have altitude hold. I can select whatever altitude I want. The aircraft will remain in altitude hold, but not forever in this case because glide slope is armed. So if the glide slope comes center, glide slope will go green. And so the glide slope is approaching. We are one dot below at this stage. So very shortly, glide slope will become green, and I will start descending with the glide.
Paolo's Pilot Lounge. Like and subscribe now.
This brings us to the end of the Autopilot video. Thank you for your attention today. Before closing this video, I want to remind you once again that the correct position to look at the autopilot status is the FMA. The importance of always reading and understanding, and the importance of continuously monitoring the autopilot status on the FMA cannot be overemphasized. It's probably one of the most critical items during any pilot training. So make sure that you keep the FMA constantly into your scan during autopilot operation.
Today we have seen that we needed to add an additional item, which was the control of thrust, which is very important, and is also very important to understand the control of thrust is actually an output for the autopilot. It's not part of the autopilot system, and therefore when something is an output, the computer itself does not know how the output system is actually performance. Yeah, there will be some output concerning this performance, but how is the autothrottle actually performing is not part of the computation of the autopilot, and that's an important piece of knowledge for a pilot. Good, I will see you at video number 4, where we will talk about the automatic control thrust. For the moment, thank you for your attention. I will see you soon on the next video. Thank you for your like and subscribe, and goodbye.